Hello, everyone. Today, we will introduce a software hardware framework for AI-driven approximate nearest neighbor search utilizing CXL memory pool. Before moving on to the main talk, let me summarize the talk in a single slide. Approximate nearest neighbor search is widely used in diverse products and services, such as search engine and recommendation systems. Basically, the algorithm finds objects that are similar to the query. This can be used to find data that matches the user search intent or to find items that most matches the user's taste. However, ANNS is a challenging workload. In production level, it often handles billion-point dataset requiring terabytes of memory. CXL can be a promising solution for scalable ANNS, but it yet shows a limited performance due to its far memory-like characteristics. Therefore, we propose a software-hardware collaborative approach to overcome the shortcomings of CXL. Specifically, it caches the frequently accessed data and selectively offloads the computation to reduce the data transfer overhead. We can compare our system against an Oracle system that has no problem with large memory requirements by having unlimited local DRAM capacity. And the results showed that CXL-ANS exhibits 3.8 times better performance than the Oracle system. I'll start the main talk by introducing our target research domain and its challenges. Dense retrieval has taken on an important role and provide fundamental support for various services such as search engines, recommendation systems, and database. Traditional string-based search retrieves data that simply includes the given keyword, which does not always match the user's search intent. In contrast, dense retrieval compares the similarity between different objects and retrieves the objects that are the most similar to a query. This new method provides a better result that matches the search intent. To compare the similarity of different objects, dense retrieval uses feature vectors that embed data and query into points in a several hundred dimensional space. These feature vectors are managed in a continuous memory space as an embedding table. Then it compares the distance between the query vector and the data vector. For example, it can measure the distance by calculating the length of the line between 2 points. Finally, it retrieves the given number of the nearest data vector to answer the query. The nearest data vector are called k-nearest neighbor or KNN. This dense retrieval provides an accurate search result. However, it is a costly operation taking a linear line to calculate the distance for every data vector. This makes dense retrieval with a billion-point dataset infeasible. So, modern dense retrieval employs approximate nearest neighbor search, or ANNS. ANNS restricts a query vector to search only a subset of neighbors with a high chance of being the nearest ones. While there are several ways for ANNS, graph-based ANNS are the most widely used approach, achieving state-of-the-art accuracy and performance. Let me provide a brief background on how graph-based ANNS works. Basically, the ANNS visits the nodes near the query by traversing the graph towards the query. It starts the search by visiting the entry node of the graph. The entry node is designated as a node at the center of the high-dimensional space at the graph construction time. This choice minimizes the number of nodes to visit during the search. Then for each neighbor node, ANNS calculates the distance between the node and the query. The calculation result is used to determine a node that is the nearest to the query and is unvisited. Then ANNS moves to the determined node to approach the query. This process is repeated to find the nearest node to the query. After finding the nearest node, the ANNS gets further from the query to visit the unvisited nodes. If this continues, the search is terminated and it retries the k number of nearest nodes among the visited nodes. While this graph-based ANNS exhibits high accuracy and performance, it is a challenging workload since it gives significant memory pressure to the system. For example, multiple production-level systems for Microsoft and Alibaba adopt billion-point datasets. They require tens of terabytes of working memory space, even just for their embedding table. It will be larger if it includes a graph. To address this problem, there have been multiple studies, and we classify them into two approaches. The first approach reduced the memory consumption by compressing the embedding table. However, the compressed embedding table makes errors during distance calculation, which degrades the search accuracy. We observed that compressing the table by only a factor of 3 already degrades the accuracy below the guided requirement from the industry. Another approach stores the graph and the embedding table to the underlying SSD. To reduce the slow storage access, they use a simplified dataset that fits in a memory. It helps reducing the search space before searching through the graph stored in the SSDs. While this can successfully reduce the storage access, the remaining storage access at the final search still significantly degrades the performance. We observed that these approaches show 47 times higher latency compared to one in-memory scenario. To avoid the accuracy drop and performance deployment, this work advocates to have billion-point datasets in a scalable CXL memory pool. Let me give you a quick introduction to how CXL can provide large memory space. CXL is an open industry standard interconnect. It supports 3 protocols, which can expand the memory over the existing PCIe physical layer, CXL.io, CXL.cache, and CXL.mem. The difference between the protocols comes from how they consider the PCIe attached device. For example, CXL.io considers the device as an I/O device. It aims to enumerate and configure the underlying endpoints, and is basically the same as the PCIe standard. On the other hand, CXL.mem considers the device as another working memory. It allows the host to access the internal memory of the device with low store instructions over PCIe. Based on which protocols are used for the main communication, CXL endpoints can be classified into 3 types. In this work, we focus on type 3 device. The type 3 device uses CXL.io and CXL.mem. Although it has no interface for a device-side compute unit, it makes the best fit for memory pooling. In particular, Type 3 device exposes its internal memory to the CXL CPU's physical memory space. The exposed internal memory is called host-managed device memory, or HDM, while the physical memory space is called host physical address, or HPA. This is just like how local DRAM is mapped to the physical address space. Thus, the applications running on the CXL CPU can access the HDM through the conventional memory instructions like load and store. Thanks to this feature, CXL CPU's memory hierarchy treats the HDM request in the same way as local DRAM requests. So, ANNS can enjoy the expanded memory space by simply placing all the billion-point graphs and embedding tables to the underlying endpoints HDMs. However, such a simple method is not yet an appropriate option for practical billion-scale ANNS. This is because the CXL's far memory-like architectural characteristics. In particular, every memory request needs a CXL protocol conversions from memory request to CXL packet called FLIT at both the host root complex and endpoint CXL controller. This memory to FLIT conversion is also required for the corresponding response, thereby having long latency for graph and vector accesses. In our analysis, using billion-point ANNS datasets, we observed that this memory to FLIT conversion makes the CXL-based ANNS 3.9 times lower. This is not acceptable for memory latency sensitive applications like recommendation systems and search engines. Our goal is to solve the aforementioned problem and further make CXL-augmented ANS faster than non-worker system. What I mean by a worker system is a hypothetical system with unlimited local DRAM capacity, thereby having no problem with large memory requirement. By making our system faster than the Oracle, we can show that our system has high scalability and high performance. It also does not show any accuracy drops since it needs no compression. To achieve our goal, we made two observations on ANNS. The first one is the node level relationship. This figure shows ANNS processing three different queries by traversing the graph from the entry node toward the query. Since the entry node is fixed and ANNS traverses the node one by one via edge hoops, the nodes closer to the entry, called inner nodes, are accessed for every query processing. In contrast, the nodes that are far from the entry, called outer nodes, are hardly accessed unless it is very close to the query. This characteristic is also observed while processing 1,000,000 KNN queries. We can see from this figure that as the number of hoops from the entry at the x-axis increase, the busy count at the y-axis significantly decreases at a log scale. So we come up with the idea of caching inner nodes in local memory rather than CXL memory space to provide faster memory access. The second observation is about distance calculation. The distance calculation consists of an embedding table lookup that retrieves the neighbor's vector and the computation. To find out the bottleneck of ANS, we analyze the execution time using the billion point data sets on Oracle system. As a result, we observe that memory access time for embedding table lookup, including the data movement from DRAM to cache, accounts for 67.6% of the total execution time. Based on this result, we can expect that if we simply place the embedding table to the CXL endpoint and calculate the distance in CXL CPU, the execution time would be dominated by the heavy data transfer overhead of the data vector. However, we observe that there is a chance to avoid such heavy data transfer overhead. Since the output distance is a scalar, it is 147 times slower than the input data vector. Thus, we come up with the idea of calculating distance in the CXL endpoint, which can significantly reduce the amount of data transfer. Now, I'll explain our CXL-ANS that employs the aforementioned two ideas to address CXL's limited performance. We propose CXL-ANS, a software-hardware collaborated approach for high-performance ANNS. Overall, CXL-ANS consists of root complex side software stack and an endpoint side hardware stack. The root complex side software stack mainly consists of query scheduler, co-manager, and corner driver. At the top, query scheduler orchestrates the ANS execution. It splits query processing into subtasks and assigns them to different hardware. In particular, graph traverse subtasks are performed at the CXL CPU side, whereas the distance calculation is performed at the endpoint side. Manager manages the CXL memory space and caches the graphs in local memory. Lastly, the corner driver manages the underlying endpoints and their address space. On the other hand, the hardware stack provides a large memory space while accelerating the distance calculation inside the endpoint. Overall, it includes domain-specific accelerator and the register for the interface, in addition to the essential hardware components for CXL-based memory expander. Next, let's dive into the details of our design, in particular for the graph local caching and endpoint side acceleration. The goal of local caching for graph is to cache the inner nodes in local DRAMs while placing other nodes in CXL memory space. To this end, we need to answer two questions. First, how can we distinguish inner nodes from the outer nodes? Second, how can we place the nodes in an appropriate memory space? To distinguish the inner nodes, Panmnesia counts how many edge hops exist from the fixed entry node to each node by leveraging single-source shortest path algorithm. In brief, it traverses the node in a brute-force manner while updating the hop count to the minimum. Then the pool manager sorts the node based on the hop count in ascending order. Finally, it allocates the node from the beginning to local DRAMs as many as it can. The allocated nodes are classified as inner nodes. To store the graph in the CXL memory, CXL-ANS maps CXL endpoint memory to the virtual address space and then allocates the memory space for the graph. To this end, at the PCIe enumeration time, our kernel driver retrieves the base address and the size of the HDM. This is done by checking the PCIe configuration space of the endpoint device. Then our pool manager allocates its HDM to different places of user level virtual address space. Finally, the pool manager allocates the virtual memory to the graph data using its memory allocator. Our memory allocator for the graph works similarly with Linux body memory manager. The difference is that we keep an allocator for each of endpoints. This allows us to balance the load by allocating each host node across different endpoints in a round-robin manner. Next, I'll explain how we can enable the acceleration in Type 3 endpoint. While Type 3 device makes a good fit to memory expansion, it has no interface for the device side component. Thus, we need a new interface that can exchange the command and the result between endpoints and the host. There are two considerations for the interface design. First, are the commands that host writes can be immediately visible to the accelerator. Second, since we have multiple endpoints, CPU intervention per endpoint should be minimized. To address our first consideration, our interface registers accept the command via CXL.io. They are mapped to the host non-cacheable PCIe space in bar, such that writes from host are immediately visible to the DSA. To address the second consideration, our interface registers handle only the event of command arrivals from CPU called doorbell. Upon doorbell, our CXL engine pulls the corresponding OP code and essential data for the distance calculation from the CPU side local DRAM. This method can save the time for CPU moving the data to each endpoint interface registers. To use this interface from the host side, our kernel driver allocates doorbell region mapped to PCIe bar. It also allocates other essential buffers in the local DRAM. By writing or checking this buffer, we can exchange the command and the data between the host and the endpoint device's accelerator. Note that in our design, all the buffers are allocated to user-level virtual addresses to minimize the number of context switches. The architecture of the accelerator for the distance calculation is shown here. Considering the formula of widely used distance matrix, our accelerators have subtractors, multipliers, and adder tree. The subtractors and multipliers process the element-wise operation in parallel. Then the adder tree accumulate the result of element-wise operations to calculate the final output. On the other hand, if we simply put the entire feature vector in a single endpoint, the backend DRAM bandwidth can be the bottleneck. This is because each feature vector is encoded by high-dimensional information. To utilize all the available DRAM bandwidth in the CXL memory pool, our pool manager charts the vectors column-wise and stores different parts of the vectors across the different endpoints. Each endpoint then simultaneously computes its self-distance from the split data vector that the endpoint accommodates. Later, the CXL CPU accumulates the self-distances to get the final distance value. Lastly, I'll introduce our evaluation results and conclude the talk. Given the lack of publicly available CXL system, we constructed and validated the CXL-ANS on an FPGA-based real system. The prototype used one CXL CPU connected to 4 CXL endpoints via a CXL switch. Unfortunately, the prototype system does not offer the flexibility needed to explore various design spaces. As a remedy, we also established a hardware-validated full system simulator that models CXL-ANS. This replicates all operational cycles extracted from the hardware prototype and is cross-validated with our real system. We use this simulator for our evaluation. For the overall performance, we compare the throughput of the various systems, including Oracle, that have unlimited local DRAM capacity. We varied the number of neighbors to find K for each dataset to represent diverse applications of ANNS. We set the accuracy requirement of ANNS following the guidelines from the benchmark. First, the compression approach fails to meet the accuracy requirement for 7 word code we tested because of its loosey compression for the data vectors. Hierarchical approach shows significantly lower performance than Oracle due to the slow storage access. The baseline CXL system shows much higher performance than hierarchical approach, but it still has room to be improved due to fleet conversion overhead. In contrast, acceleration in endpoint significantly improves the performance and is also faster than the Oracle system. This is because it minimizes the data transfer overhead for the data vectors. Lastly, local caching for graph shows further improvement by reducing the CXL memory access for the graph traverse. To dig deeper, we directly evaluated the effectiveness of our ideas. On the left, we can say that local caching for graph exhibited 59% hit rate for billion point datasets with only 128 GB of local memory. On the right, we can say that the acceleration in the endpoint successfully reduced the amount of data transfer by a factor of 21. As a conclusion, we propose CXL-ANS, a software-hardware collaborated approach for scalable ANS. It places all the data sets into CXL-based disaggregating memory pool, thereby having high scalability. Further, it caches the frequently accessed nodes in local DRAM to reduce the slow CXL memory address. It also accelerates the distance calculation in the CXL endpoints to reduce the data transfer overhead. As a result, CXL-ANS exhibits 3.8 times better performance than the Oracle system.